send you a link and you can just forward it to me.
Okay, great.
And you'll also have it. All right, great. It is absolutely my pleasure to introduce Dr. Adi Foord. She did her undergrad at BU in Boston, naturally, and went to grad school at the University of Michigan, where she worked with Kaihan Gultekin. And she graduated, defended her PhD this past June, and she's now the Porat postdoctoral fellow at Stanford University. She is the person that I ask anytime I need to know something about X-rays, and she's an expert on dual-AGN. So I give you a D to talk about her research. Thank you.
Great. Okay. Can you see the slide across the full screen? Okay, great. All right. Thank you, Jessie, for that really kind introduction. I'm excited to be remotely presenting on some of my work today. The title of my talk is Discovering the Missing Population of AGN Pairs with Chandra. So I hope by the end of this talk, you have a better idea of what AGN pairs are, why the population is perhaps missing, and my efforts to discover more of them. And the background of this slide actually shows Chandra observations of a handful of AGN pairs that I've discovered, and they'll all make brief appearances throughout the talk. Oh, I also just want to note that obviously feel free to interrupt me whenever you have questions, or you can post a question in the chat, and maybe Jessie could let me know if there's something there. Okay. So I'll begin with reviewing what binary and dual-AGN are and how we detect them. I'll then introduce you to my code BAYMAX, which stands for Bayesian Analysis of Multiple AGN in X-rays. This is a tool that I developed while at the University of Michigan. So I'll review the Bayesian framework behind it. For those of you who don't know, BAYMAX is also this friendly robot from the Marvel universe. So this is the logo for the code. So you'll be seeing the character on a couple of the slides. I'll then talk about results using BAYMAX, and in particular, recent papers which utilized it, as well as ongoing work that I'm using the code for, including using it for research beyond just dual-AGN. And then I'll quickly show some future work that I'm really excited about. So we believe that galaxy mergers lead to dual and binary supermassive black holes. So in this scenario, you have two massive galaxies, each with their own central supermassive black hole, and they are in the process of merging. So over time, you may expect dynamical friction to drag the two supermassive black holes toward one another. And during the phase of the merger where you have two supermassive black holes, they are kiloparsec scales apart. They're not yet gravitationally bound. And dynamical friction is the main mechanism of energy loss. You can classify the system as a dual supermassive black hole system. With time, you may expect the two black holes to continue moving toward one another, and they may eventually become gravitationally bound. So in this phase of the merger, the two black holes are parsec scales or less apart from one another. And the main mechanism of energy loss is now three-body interactions with nearby stars. And in this phase of the merger, you can classify it as a binary supermassive black hole. And then eventually, you may expect the two black holes to get close enough to one another that gravitational radiation dominates as the main mechanism of energy loss, and the two black holes may coalesce. So for both the dual supermassive black hole phase and the binary supermassive black hole phase, when both of your black holes are actively accreting, you can classify the systems as dual-AGN and binary AGN. So most of my work focuses on the dual-AGN population. And we expect dual-AGN to be a result of galaxy mergers. And we know that galaxy mergers are quite ubiquitous in our visible universe. However, to date, the number of confirmed dual-AGN remains quite small. So there's really only a handful of confirmed dual-AGN to date. In this figure, I'm showing the confirmed dual-AGN from the literature, where the marker denotes the detection wavelength, and I'm plotting the projected physical separation between the two versus their redshift. And then I'm also including some of the various telescope sensitivities on the figure as well. So as you can see, there's less than 40 confirmed dual-AGN to date. Most confirmed dual-AGN are X-ray detections, and most confirmed dual-AGN have physical projected separations greater than a kiloparsec. So it's really too bad that the dual-AGN population is so small, because in fact, studying dual-AGN will give us a lot of insight into things such as supermassive black hole growth and evolution, as well as the growth and evolution of the host galaxies. So on a larger cosmological context, quantifying the rate of AGN pairs will represent a lower limit on redshift-dependent merger rates and the occupation fractions of dual supermassive black holes and galaxies. And this is a plot showing the fraction of dual AGN as a function of redshift. And this is taken from the Eagle hydrodynamical simulations. And it's a project that I'll briefly highlight near the end of this talk. And then additionally, quantifying the rate of AGN pairs has implications for timescales for post-merger dynamical evolution. So this plot is showing the various timescales associated with an AGN pair as it moves through the dynamical friction phase, into the three-body interaction phase, into the gravitational wave phase. The gravitational radiation phase. And there's still a lot of unknowns regarding all of these timescales. And then just in general, finding more dual AGN can help answer longstanding questions, such as whether galaxy mergers trigger accretion onto supermassive black holes. And here, observational evidence remains inconclusive to date. On top of this, it's been shown in simulations that only the most massive supermassive black holes are triggered by mergers, whereas less massive black holes are instead triggered by intrinsic processes. And this is a figure taken from one of my projects where I analyzed the lowest mass dual AGN candidate to date. And then lastly, it will allow us to answer the question of how the activity of merging AGN regulates the growth of the host galaxies. So these are simulations of resultant galaxies after a merger with various mass ratios. And the top panel are simulations that included AGN, while the bottom panel are, the top panel are simulations that did not include AGN, and the bottom panel are simulations that did include AGN. So you can see that without an AGN, the resultant galaxy doesn't really seem to care about its merger history. While when you had two AGN, the resultant galaxy looks different in each mass ratio case. And for the major mergers, the resultant galaxy has ceased all star formation and has kind of become this red and dead elliptical galaxy. So as we start to expand the known population of dual AGN, we can start to try to answer these questions. So most observational evidence for AGN pairs relies on optical spectroscopy and photometry. And one of the most popular detection techniques is searching for double peaked emission lines. So the idea behind this detection technique is if you have two galaxies, they're in the process of merging and they both host an AGN. If you take a spectrum of the system that includes both nuclei, you may expect to see this double peaked emission characteristic corresponding to emission associated with each respective narrow line region. And you can expand on this analysis and actually try to spatially resolve, and I'm circling that with my mouse right now, spatially resolve where each emission component comes from. And then you can see if the two regions coincide with two galactic nuclei, for example. There are caveats with this type of analysis. And in particular, you do expect double peaked emission lines for things besides just dual AGN. And so for any dual AGN candidate that is found using this technique, you really want follow-up with X-ray or radio observations to confirm the true accretion nature. So the idea is that you can confirm a dual supermassive black hole system observationally if both black holes are actively accreting and if you have the necessary resolution. So with radio observations, you can resolve systems on the smallest scales. And on the left-hand side, I'm showing a figure taken from Banzel et al., where they used the VLBI, which is radio observations, to detect what they were claiming was a binary AGN. So C1 and C2 are the two radio cores, and they're attributing the emission of those cores to 2-AGN. And with the VLBI, they are able to resolve this system where the projected physical separation was around 7 parsecs. So that's quite small. If you're going to be using X-rays to search for dual-AGN, you really want to use Chandra because of its superb angular resolution. So on the right-hand side, I'm showing a dual-AGN that was found by Mike Koss. And the figure on the left is the optical image of the merger. And I'm overplotting the two Chandra detections in red. And if you compare this field of view to XMM's field of view, which is another X-ray based telescope, you can see why in this case, it was really necessary that you have Chandra to find the system. That being said, Chandra was only able to find this system because the angular separation is around 6 arcseconds, which is much larger than Chandra's nominal resolution of an arcsecond or so. And so unfortunately, as the angular separation of your 2-AGN nears that instrumental PSF, it'll become very difficult to resolve it even with Chandra. So I'm showing you on the left-hand side a simulation of a single point source as seen by Chandra. And on the right-hand side, I'm showing you a simulation of a dual point source system as seen by Chandra. And the separation of the dual point source simulation is 0.3 arcseconds. So by eye, you can tell it's really hard to discern the single point source from the dual point source system. And so currently we're really resolution limited in our efforts to find these AGN pairs in the sky. So this issue was the motivation for my thesis when I was at the University of Michigan, where the development of a tool that could analyze a Chandra observation and tell you the likelihood that you are looking at one versus multiple things would be extremely useful. And thus I developed BAYMAX, and BAYMAX allows for this statistical analysis on Chandra observations. It does so using a Bayesian framework, as you could guess, namely Bayes factor. And I'm showing the analytical form of Bayes factor on this slide. So Bayes factor represents the degree to which you're favoring one hypothesis over the other. And so for all of my analyses on dual-AGN candidates, I'm comparing a single point source model to a dual point source model. And values greater than or less than 1 will tell you which model is favored. And so within each of the integrals, you have your likelihood densities and your prior densities. So I'm highlighting the likelihood density right now. BAYMAX calculates the likelihood densities by generating likelihood models. And it does this by modeling the unique PSF for a given observation. And we can do this because there's a software called MARCS that contains detailed models for Chandra's high resolution mirror assembly. And then regarding the prior densities, which I'm now highlighting, examples of parameters in the prior vectors for the dual point source model includes the spatial XY position of each point source, as well as the count ratio, which I'm going to be denoting by this parameter F. And the count ratio represents the number of counts the secondary has with respect to the primary. And another parameter is the background fraction. So this is the number of counts associated with the background with respect to the number of counts associated with a point source component. So once you've generated likelihood models for single and double point sources and you've defined your priors, which these can be either user-defined or non-informative, BAYMAX goes ahead and calculates the Bayes factor via a technique called nested sampling. If you remember, Bayes factor is a ratio of integrals, and the number of dimensions that you're integrating over is equal to the number of priors that you have. So when you have 4 or more priors, it actually becomes very difficult to calculate those integrals in a timely manner. And so nested sampling is just an MC sampling technique that allows you to more efficiently sample from likelihood space. And it allows the code to estimate Bayes factor on the order of minutes to hours instead of years. And then Lastly, using an MCMC algorithm, PyMC3, the maximum likelihood of parameters and their uncertainties are estimated. So this is a fun slide to show because it allows me to quiz my audience, which has become a little bit more difficult as these talks are now remote. So feel free to speak up. But in any case, these are 10 simulations. All of these are observations as seen by Chandra. Half of these are single AGN and half of these are simulations of dual AGN. And I'd like to see if anyone can correctly identify the dual AGN simulations. So feel free to speak up.
I feel like my first answer is no. I don't feel like I can.
Yeah, it usually gets really quiet during this part of the talk because no one knows. But I mean, that's obviously exactly the point, right? It's very difficult to discern the single point sources from the dual point sources. And so if no one wants to share their thoughts, that's completely fine. I can just show you the true dual point source models.
Oh, I can take a stab at it. Too late.
No, go ahead.
Well, I want to know what your answer was.
I was going to say 1, 7, 8, 10.
Wow, okay.
And maybe 5.
All right, you did quite well. Not bad at all. 1, 7, and 10 are.
That is not very good. I didn't do very good.
Well, better than most, I will say. So I'm highlighting the dual AGN simulations in the black boxes. And BAYMAX was able to correctly identify each of these simulations being likely composed of 2 versus 1 thing. So I want to highlight that BAYMAX can do quite well both in the low count ratio and the low separation regime. So if you look at panel 1, the separation, which is denoted by R, is quite large. It's 1 arcsecond, but the count ratio is quite small. So with 100 total counts, the secondary is contributing around 9. If you look at panel 3, on the other hand, the separation now is less than 0.5 arcseconds, but the count ratio is much larger. And so in general, to probe the smaller separations, you'll need larger count ratios and vice versa. And it, of course, also depends on the total number of counts that you have. So I'm now going to review a couple recent analyses that I used BAYMAX on various samples of multi-AGN candidates. So the first sample that BAYMAX analyzed was 12 dual-AGN candidates. And each of these systems were dual-AGN candidates based on double-peaked narrow O3 emission lines that were found in their SDSS spectra. So that's using that technique that I spoke about earlier in the talk where you're looking for the double-peaked characteristic in the optical spectra. And so each of these systems received follow-up observations with long-slit spectroscopy, and that allowed you to actually spatially resolve where each O3 emission component resided. And so the inclusion of this optical information allowed for informative priors during the X-ray analysis. So here I'm showing you the optical images of these 12 candidate dual AGN. And in the red and orange boxes, I'm showing the location of our informative priors. And that was based on where that O3 emission was found to spatially reside. So each of these systems received follow-up Chandra observations, which I'm now showing you. And once again, in the red and orange boxes, I'm showing the locations of our informative priors for a primary and secondary X-ray point source. And I will also add that we ran BAYMAX on all of these systems using non-informative priors. And so in that case, the primary and secondary were allowed to be anywhere within the fields of view that you see for the observation. So just jumping straight to the results, 4 systems were found to have Bayes factors that strongly favored the dual point source model. And for each of these systems, I'm showing you 2 different figures. So on the left-hand side, I'm showing you the unbinned X-ray data. I'm showing you the unbinned data because BAYMAX can probabilistically assign each count to a different model component. So for the dual point source model, Your various components are your primary point source, your secondary point source, and then some type of background contribution. So the counts that are plotted in red-filled circles are those most likely associated with the primary point source. Those in open-faced squares are the counts most likely associated with the secondary point source, and those in faded triangles are likely associated with the background. One of these systems, which I'm now circling with my mouse, had this diffuse emission component that you saw both in the X-rays and in the optical data. And so we included an additional model component to account for that emission. And the counts that are in blue diamonds are those that are most likely associated with it. The red lines are showing the 95% confidence intervals for the locations of the primary and secondary. And then on the right-hand side, I'm showing you the joint posterior distributions for separation and count ratio. So because BAYMAX can probabilistically assign each count to a different model component, one can actually sample from the posterior distributions and create many different spectral realizations of each component. So this is really cool because the spectral analyses with BAYMAX represented one of the first that could individually analyze spectra of closely separated X-ray components. And a spectral analysis is also very useful because you can analyze things such as the flux ratio, whereas the posteriors returned by BAYMAX gives you information on the count ratio. So this is an example for one of the mergers in the sample. This is the merger that had that diffuse emission. So you see it here in the X-rays, and you also see it here in the optical image. And in the lower panels, I'm showing 1,000 spectral fits to 1,000 spectral realizations for the primary X-ray point source and the secondary X-ray point source. And I'm overplotting one of those spectral realizations in black. Oh, I will also just note, since I'm not sure if this is a heavy X-ray audience, it's likely not. X-ray astronomers like to fit most things with power laws. And so these X-ray spectra are also fit with power laws where the units are in counts per second per keV. So what I did for this sample is I defined an AGN luminosity criterion where the 2 to 7 keV luminosity needed to be greater than 10 to the 40 ergs per second. And if either the primary and or secondary did not meet this luminosity criterion, I would not classify it as a dual AGN. The idea being that at X-ray luminosities below this value, you're susceptible to contamination from other X-ray sources that aren't AGN, such as X-ray binaries. So returning to these four systems, I carried out the spectral analysis, and I found that there were two that had a primary and secondary that met that AGN luminosity criterion. One of the sources was that merger that had that diffuse emission, and so I carried out an additional analysis where I compared the spectrum of the secondary to the spectrum of the diffuse emission. The idea being that that secondary could represent some dense clump of material that was also the material that made up that diffuse emission. And so I couldn't discern between the two spectra at a high enough confidence level. And so conservatively, we did not classify that system as a dual AGN. And we were left with BAYMAX confirming one dual AGN in the sample. So in addition to the X-ray analysis, complementary multi-wavelength observations give you insight into the preferential environments of AGN pairs. So of the original 12 systems, I looked at a subsample of 6 that were visually identified as merging in their HST data. And I'm showing you that subsample on the left-hand side. So this subsample includes the 2 mergers that had a primary and secondary X-ray point source that met that AGN luminosity criterion. And so one of the things I looked at was how the extragalactic hydrogen column density varied as a function of the physical separation between the 2 galactic nuclei. This NH value is something that you can fit for through the X-ray spectral fits, and it measures the gas density that's immediately surrounding the AGN. So I won't call it a trend because there's only 6 points on this figure, but I will say that the data suggests that AGN pairs may prefer closely separated and gas-rich environments. And this is something that simulations have found as well. In addition, I attempted to carry out spatially resolved BPT diagnostics. So BPT diagnostics are narrow emission line ratio diagrams that are used to distinguish the ionization mechanism of the gas. So it's an optical diagnostic for seeing whether or not you have an AGN. So this is a BPT diagram for the two systems that had a primary and secondary that met that AGN luminosity criterion. And for one of the systems, which I'm now highlighting, it was possible using the available long slit data to actually decompose the two X-ray point source components in velocity space, given the optical spectrum. And so I could carry out a spatially resolved BPT diagram for each nucleus. So the bigger square here is the primary and the smaller square is the secondary. So I found that both regions have emission consistent with ionization from an AGN, and it supported the results from the X-ray analysis. For both the analysis that I'm showing you here and the analysis that I showed you on the previous slide, these are obviously things that I plan to do in the future with much larger samples so that you can actually start confirming trends in the data, and you can actually start comparing various AGN diagnostics across multiple wavelengths. So the most recent analysis that I used BAYMAX on was analyzing a sample of nearby triple galaxy mergers to search for potential triple AGN systems. So triple supermassive black hole systems are an interesting subset of the multi-supermassive black hole population. And in particular, the presence of a tertiary black hole is believed to be able to shrink the inner binary semi-major axis, increasing the eccentricity of the orbit, which you're kind of seeing in this little Python simulation I made. And it perhaps will allow that binary supermassive black hole to merge on faster timescales. And in addition to this, triple AGN are expected to be relatively common. So a recent study on illustrious supermassive black hole binaries, illustrious is another hydrodynamical simulation, found that over 30% of AGN pairs undergo subsequent merger events over a large range of redshift. However, to date, there's only been one serendipitously discovered X-ray triple AGN, and this is a figure taken from the discovery paper. It got a lot of press in early 2020, so this might be a system that some people in the audience are familiar with. So all of this motivated me to create a sample of nearby triple galaxy mergers to carry out the first systematic X-ray search for triple AGN. So although the larger goal was definitely to find more triple AGN, these are rare and exciting systems. More importantly, I was interested in measuring how many AGN each triple merger had and seeing if those numbers connected to environmental properties as measured in the IR emission by the WISE telescope. So all triple galaxy mergers were visually identified in SDSS, and each nucleus was required to have a spectroscopic or photometric redshift that were consistent with one another to ensure that it was truly an interacting system. Of this larger sample, 7 were found to have archival Chandra data available, and I'm showing you the optical images for those here. This sample includes that one serendipitously discovered triple AGN system, which allowed me the opportunity to reanalyze the Chandra data using a more robust technique. So here I'm showing you the Chandra X-ray observations. And once again, in the boxes, I'm showing you the location of the informative priors for the primary, secondary, and now tertiary X-ray point source. And because I was searching for possible triple X-ray systems, I was now calculating the Bayes factor for 2 versus 1, as well as for 3 versus 2. And similar to the analysis I showed you earlier, all of these observations were also analyzed using non-informative priors. So there, the location of the point sources could sit anywhere within this field of view. So excitingly, 4 new dual AGN were discovered through this analysis. And similar to earlier, on the left-hand side, I'm showing you the unbinned Chandra data, where the counts most likely associated with the primary are shown in yellow circles, and those most likely associated with the secondary are shown in open-faced purple squares. I'm also overplotting the SDSS optical image contours that you're seeing in that brown/pink contour. And then on the right-hand side, I'm showing the joint posterior distributions for separation and for count ratio. So interestingly, in past analyses of 2 of these sources, they were classified differently. So one of these systems was previously classified as a triple AGN using optical diagnostics, and one was previously classified as a single AGN system using X-rays. So these past mismatches and classifications reflect why X-ray analyses, and in particular analyses with BAYMAX, are really important for better understanding the true number of AGN in these mergers. So I carried out a spectral analysis similar to before to evaluate the X-ray luminosities of each point source detected by BAYMAX. And here I'm showing the individual spectral fits for the primary and secondary AGN in one of the dual AGN systems that I found. And this is a really fun example to show because BAYMAX found and fit for its first iron K alpha line. This is an emission line that you see in many X-ray spectra of AGN. So similar to before, I defined this AGN luminosity criterion of a 2 to 7 keV luminosity greater than 10 to the 40 ergs per second. And as well, in order to be classified as an AGN, it had to have an X-ray luminosity greater than what you might expect from the X-ray binary population in the respective host galaxy. I was also able to confirm the triple AGN nature of that one serendipitously discovered triple AGN. So next to the figure from the discovery paper, I'm showing the joint posterior distributions for the northwestern and southwestern AGN, which are galaxy 3 and 2 respectively in that discovery paper figure. And then I'm now replacing that figure with the results from BAYMAX, where once again, the counts are plotted with different markers or colors, depending on which model component they're most likely associated with. So this was a really great sample to analyze because the triple mergers ended up having a really wide range of X-ray AGN activity. So all the way from likely having no X-ray AGN, all the way up to having 3 X-ray AGN. And so this variety allowed me to look into possible links between X-ray AGN activity and differences in their environments as measured by the WISE telescope, which observes in the mid-IR band. So in particular, I looked at levels of obscuration in each system using those mid-IR observations supplied by WISE. So on this slide, I'm showing a WISE color-color diagram. This is a diagnostic used to select highly obscured and highly luminous AGN from star-forming galaxies. And you can do this because of the differences expected in the spectral energy distributions of AGN and galaxies without AGN. And so I'm showing you that in this little GIF I made on the left-hand side, where the WISE colors are changing based on the type of spectral energy distribution that you have. So because of these differences, a lot of color cuts have been defined, and I'm showing you 2 with these blue lines, above which you might expect an AGN to reside. And so I'm plotting the WISE colors for a subsample of these triple mergers that had suitable WISE coverage. And next to each point, I'm saying how many X-ray AGN were discovered in those systems. So as you can see, not all of the systems would be identified as AGN using these IR diagnostics. I also looked at how the WISE1 minus WISE2 color varied as a function of the extragalactic hydrogen column density. So once again, that's a parameter you can fit for through the X-ray spectral fits. And a larger WISE1 minus WISE2 color means that the system is more red. So I found this trend where with increasing W1 minus W2 color, you had an increasing NH. And this is likely reflecting how the motions of gas and dust are coupled in these merging environments, where large amounts of both of them can be efficiently funneled into the active central region. And interestingly, I found that that one triple AGN system that I'm circling with my mouse had the highest levels of both NH and W1 minus W2 color, while all of the dual AGN had lower levels. So given that supermassive black holes grow and ignite to AGN through the accretion of cool gas, it's possible that triple merger systems with higher levels of nuclear gas may have more AGN. So similar to before, these types of trends are something I want to investigate more in the future with larger samples. So I'll be applying for more Chandra time this upcoming spring for other triple galaxy mergers that don't have archival Chandra data. Okay, so moving on to some other work, I want to highlight that BAYMAX can be used for so much more than just multi-AGN systems. Really, anytime you're interested in whether your X-ray image is composed of one or multiple X-ray point sources, you can use BAYMAX. So recently, BAYMAX was used to analyze the X-ray emission of this high redshift quasar. And this was a project that was led by Kate Napier, who is a graduate student at the University of Michigan. And without getting into the specifics, this is a peculiar case of a high redshift quasar that has bright radio emission from the lobes. And some of the main questions of the analysis were whether the lobes were X-ray emitters as well, and if they were, what were their X-ray luminosities. So on the left-hand side, I'm showing you the VLBA image of the source, and you can see that there is emission from the core as well as from the two lobes. And on the right-hand side, I'm showing you the actually very deep Chandra observation of the source, where there was only about 60 counts detected. So because there's only about 60 counts, it's really hard to tell by eye whether or not the X-ray emission is extended, and if it is, if it has a similar position angle to what you see in the radio observations. So we analyzed this system with BAYMAX, and here we were comparing a single point source model to a triple point source model. The idea being whether only the core was emitting an X-rays or the core and the two lobes were emitting together. And so jumping straight to the results, BAYMAX strongly favored the triple point source model. So once again, here I'm showing you the counts where their colors and markers are signifying which model component they're associated with. And in the boxes, I'm showing the location of our informative priors that were based off of the VLBA data. So moving forward, I'm really interested in pairing the power of X-ray and IR observations. And for dual AGN studies, X-ray and IR observations really complement one another. So in particular, for any dual AGN that's detected by BAYMAX in the X-rays, follow-up via high-res IR observations can identify stellar nuclei associated with each of the AGN. You can do obscuration measurements, as I showed you previously, and you can also do stuff like estimate the mass ratios of the galaxies. So this is really a great example of that. I'm currently working on analyzing this sample of merging galaxies that both have Chandra observations as well as high-res IR imaging via the Keck telescope. And this is a really large survey being led by Mike Koss. So here I'm showing an X-ray observation of one of the systems. It was flagged as being a possible merger due to this optical image that they had. So you see this large tidal tail, which may signify that some type of merging has happened or is ongoing. So I analyzed the Chandra observation using BAYMAX, and here I used non-informative priors. So I had no idea where a primary or secondary AGN could or would be sitting. And so now I'm showing you the results from BAYMAX. BAYMAX strongly favored the dual point source model. And in the X and the cross, I'm showing you the best fit locations of each of those components. And the exciting thing is when you compare these results from BAYMAX to the follow-up high-res IR that it received with Keck, there were two galaxies that were resolved in the same location as where BAYMAX thought two X-ray point sources were sitting. So I'm continuing to analyze other systems within this sample, and hopefully this study should be published sometime this year. Okay, so the current and future projects that I'm going to be working on while at KIPAC all focus on large systematic X-ray based surveys of dual AGN. And this is really one of the only ways that you can start exponentially increasing the number of known dual AGN and start confirming those possible trends that you see in the data between their activity and their environments. So the first project is looking at this sample of a nearby AGN, where, given how close the AGN are and given the abilities of BAYMAX, I'm going to be sensitive to any dual AGN with separations as low as 14 parsec and complete to separations larger than 250 parsec. So this is a really interesting regime of separation space where you're beginning to near the binary AGN phase. The second project is constraining the dual AGN fraction across cosmological time, which is quite a large project. And the idea here is to carry out the first measurement of dual AGN both at high redshift, but also as a function of redshift. And this will have a lot of important implications for things such as galaxy evolution through cosmic time. So I'm going to be spending my last 5 minutes or so focusing on the first project because there may be people in this audience who are interested in closely separated supermassive black holes, but I'm happy to speak with anyone after the talk or at a later time about this second project if that's something that interests you. Okay, so the idea of this project is to quantify the rate of nearby dual AGN. And the rate of dual AGN at low redshifts is completely unconstrained. So it's been estimated to be anywhere between 0.1% to as high as 7%. And this is a result of a handful of things. So one, in the past, you've had incomplete samples. And expanding on that, the dual AGN fraction is heavily dependent on the detection technique that you use. And secondly, past analyses have been sensitive really only to the largest separations and count ratios. So the largest X-ray survey to date that has looked at the nearby dual AGN fraction used the Swift telescope, which has a much larger PSF than Chandra. And they were sensitive to separations on the order of 5 or 10 kiloparsec or greater. On top of this, however, AGN observability is expected to increase as a function of decreasing physical separation between the supermassive black holes. So this is a figure taken from one of Scott Barrow's papers, where they're plotting on the y-axis the dual AGN fraction, and on the x-axis the physical separation between the two AGN. And in the purple, they're plotting the results of that nearby X-ray survey I spoke about, and in the blue, they're plotting their results from an optical survey. So you see that there's a mismatch between the X-ray and the optical surveys, which is to be expected. But you also see for both of the surveys that there's this trend of increasing dual AGN fraction as a function of decreasing separation. And if you extrapolate these trends down to separations below a kiloparsec or so, you may expect the dual AGN fraction to be as high as 10 up to 40% or so when you get down to those small separations. So that's one of the reasons why this sample is so exciting, because it's analyzing the dual AGN population where past spatial resolution limits have prevented a systematic analysis, but where the accretion rate is predicted to peak. So I created a sample of 86 nearby AGN. They're all within 150 megaparsec or so. 36 of these have archival Chandra observations, which I'm currently analyzing, and 50 will be receiving or have already received new Chandra observations, which I'm very excited about. In addition to the Chandra data, many of these systems also have follow-up observations in the near IR using 4-star observations at the Magellan-Bode telescope. So these are observations I carried out while at the University of Michigan, and these high-res IR observations allow you to resolve both large-scale and small-scale morphological features that weren't identifiable necessarily with the existing optical and IR archival data. So I'm showing you 2 examples of that. On the left-hand side for both of these systems, I'm showing my 4-star observations, where you're seeing interesting things like perhaps interacting systems, as well as things like perhaps some tidal tails. And these are features that you couldn't identify with the existing archival 2-mass data. And then just to further emphasize, this sample is really exciting because I'm going to be sensitive to these really, really small separations where you're perhaps nearing the binary AGN phase of the merger. So these are some preliminary results, very preliminary, but there are new dual-AGN candidates that are being discovered as I'm analyzing the archival and the new observations that are coming in. So these are an example of 4 of them, where BAYMAX highly favored the dual point source model for these systems. And given the angular separation and their distance from us, it corresponds to physical separations between around 400 parsec up to a kiloparsec. And so ongoing work is going to be an X-ray spectral analysis of both of the point sources, in addition to folding in information that you get from the multi-wavelength observations that are available for all of these systems. All right, so that is all I have. Thank you so much for listening to me talk for the past 45 minutes or so, and I'll take any questions.
All right, if you have questions for Adi, if you would just like to use your little raise hand button, I can look in the list. I'm gonna real quick ask a question while you all think of them. Can you try, I'm super stoked about the idea of the infrared imaging combined with Chandra. Can you do essentially what you did of picking out like mergers or multiple point sources in the optical and then asking what BAYMAX sees and skip the optical? So you just look in the infrared and see if there are, signs of multiple components in the galaxy, and then look at Chandra, and then you don't need like an optical, it can be optically obscured.
Yeah. So I think that, that's one of the strengths of using IR observations, right? You're not dependent on the spectra, which could be explained by things besides just dual-AGN, but you're also not affected by obscuration that the optical observations are. So I think, what I plan to do is to just use IR moving forward, because I think that really makes the strongest case when you combine it with the X-ray results. Yeah.
Awesome. All right, Sam?
Yeah, I have a question. The talk was really great. Thank you very much. I wondered about the criterion that you defined for the AGN cutoff, and I wondered if you investigated like how sensitive your results are to that criterion.
Yeah. So first I'll say that they had to be greater than 10 to the 40 ergs per second at the 3 sigma confidence level. And so, as your spectra have fewer and fewer counts, your error bars are really going to expand, right? And so it's really important to fold in those errors, because it might be easy for something with 5 counts to be consistent with 10 to the 40 ergs per second. But if it's not greater than that, given those large error bars, you shouldn't classify it as an AGN. So that's something that is an important aspect of the analysis. I feel like you had a second question and I completely forgot what it was. Can you remind me?
Just kind of, so I understand that the criterion is important, and I was wondered if you analyzed a set of data where you varied the criterion, and if there was some threshold where it would change what it decided.
Oh, I mean, yeah, definitely. So for example, if you lower that criteria, almost everything will be classified as an AGN. When you raise the threshold, so if you go to like 10 to the 41 ergs per second, for example, for the samples I've analyzed so far, the results remain the same. Moving forward, that might not necessarily be the case. Something else that's important to do besides just that criterion is to look at things like the star formation rates, for example. So if you have very high star formation rates, you might expect X-ray binaries to, very easily exceed that luminosity. So it's very much a case-by-case basis, and it's something that you need to carefully think about for each source.
Okay, thank you.
Yeah. All right, Bill?
Yeah, very, very nice talk. And you may have said this, but when you were looking at the triple candidates and BAYMAX came back and said it was a dual, Is there a way to estimate whether the third is really also a supermassive black hole, but just not an AGN, not emitting either in our direction or at all?
Yeah, so there's a lot of things. Yeah, there's a handful of things you can do. So the first case is that you might have an X-ray AGN there, but it's highly obscured, right? So the X-rays aren't getting out. And so what we did for each of those triple mergers is we estimated an upper limit on the X-ray emission that was coming from that region. And then, you know, assuming various levels of absorption, estimating what the X-ray luminosity might be. So comparing what we were detecting to what you might get with high levels of obscuration. And so for many of them, even with very high levels of obscuration, the X-ray luminosity would be below that AGN luminosity threshold. Yeah. I believe for one of them, that wasn't the case. And so there we were very careful with our language saying there might be an obscured AGN there. Other things you can do though, besides just an X-ray spectral analysis is like look at radio observations. Is it emitting in radio? You can also do, you know, optical diagnostics. So you're always comparing your X-ray diagnostics to other wavelengths and then trying to best determine if there's some type of environmental effect that's, you know, affecting what you're seeing in X-rays.
Is it unlikely at all that it might be just sort of a gas-free region it's in and it's not, you know, emitting at all, like our Sagittarius A star is or something?
Yeah. I mean, you know, most AGN aren't emitting in X-rays. So there's a large chance that there could be something there that isn't emitting. But then it isn't necessarily classified as an AGN, right? Okay. So it's a little bit different. Yeah. Got it.
Steve.
Hi, Adi. That was a great talk. Thanks so much for it. In the project you were talking about towards the end of your presentation, you were saying that you would be able to potentially measure systems as closely separated as 14 parsecs, and then way up to hundreds of parsecs as well, maybe kiloparsecs. With all of these systems being detected, will you be in a place to start sort of forecasting the demographics of these systems, and then maybe even forecasting the rates of even more closely separated systems? Like, will you be able to make comments about how they're flowing to smaller separations still?
Yeah, so there's a couple components to that. So once you start detecting things in the closely separated regime, if you have enough of them, you can start trying to extrapolate what the population looks like at that stage, and you'll start having a better understanding of the evolution from larger scales to smaller scale separations. I'm not quite sure if this is what you were getting at, but I think that something else that you can get from this study is comparing the possible merging timescales of those closely separated supermassive black holes to the look back time, and trying to get a better idea of maybe how many have merged by z equals 0, for example. And then you start linking to things like the possible gravitational wave background you should be detecting by z equals 0. So there is a lot that you can do, but at the same time, you're hoping to have more than one, right? Because at that point, you really only have a lower limit on maybe what the population represents. Yeah. Did that answer your question?
You did. Thank you very much.
All right, I think we are about out of time. Thank Adi again for joining us today.
Thank you so much. This was really fun.
All right.